Today, we're going to pull back the curtain on an invisible force that, honestly, powers just about everything, from the radio in your car to the Wi-Fi in your house. We're talking about analog modulation. It's one of those fundamental concepts that makes our connected world tick, so let's get right into it.
So have you ever been driving down the highway, you see one of those absolutely enormous radio towers, and you just wonder, why? Why does it have to be so ridiculously big? I mean, your phone has a tiny little antenna, so what gives? That question, it turns out, is the perfect doorway into understanding why we need analog modulation in the first place.
You see, it all comes down to what you could call the signal problem. The basic issue is that just trying to send raw information, like your voice or a song, directly through the air, well, it just doesn't work. Not over any real distance anyway. There are some pretty major hurdles here. For one, to send a low-frequency sound wave, you would need an antenna that's literally miles long. No joke. And even if you built it, the signal would be so weak it would just fizzle out almost instantly. Plus, imagine if every radio station just blasted their signal out at the same time. It would be a complete mess, just a jumble of noise and interference. So how in the world do we get around these basic laws of physics? Well, the solution is an incredibly clever process called modulation. And honestly, it's the key that unlocked pretty much all of modern wireless communication. At its heart, modulation is really all about giving our weak little message a ride on a much stronger, high-frequency wave. Here's a great way to think about it. Your message, the song, the voice, is like a person who can't swim very far. The high-frequency carrier signal, that's a speedboat. Modulation is just the process of getting that person onto the boat so they can travel a long, long way.
So here's how that works in practice. First, you start with your information. We call that the message signal. Then you generate a really powerful, consistent, high-frequency wave. That's our speedboat, the carrier signal. And finally, you combine them, creating what's called the modulated signal. Now your information is ready for its long-distance journey.
Okay, so it turns out there's more than one way to get our passenger onto that speedboat. In the analog world, there are three main techniques that engineers came up with, and each one is pretty unique. Let's take a look. First up, we have amplitude modulation, or AM. You've definitely heard of this one. With AM, what we do is we change the amplitude, you can think of that as the height or the strength of the wave, to perfectly match the pattern of our original message. The speed of that wave, its frequency, stays exactly the same. So if we go back to our speedboat analogy, AM is like making the boat itself get bigger and smaller in the water to represent the message. The boat's speed never changes, but its size is constantly fluctuating. The key thing to remember is the information is literally encoded in the height of the wave. Now, AM is pretty simple and cheap to build. That's a huge reason it was adopted so early and became the standard for radio for decades. But there's a downside. It takes a lot of power, and because things like lightning or noisy power lines also affect amplitude, the signal can get distorted easily. And that's exactly why AM radio can sometimes sound so crackly. Okay, next up we have frequency modulation, or FM. Now with FM, we do the complete opposite. We keep the amplitude, the height of the wave, totally constant. Instead, we encode the message by varying the frequency of the carrier wave, making it oscillate just a little bit faster or a little bit slower to match the sound.
So what does our speedboat do now? Well, it never changes size. It stays at a constant height in the water. But to carry the message, it's always speeding up and slowing down, speeding up and slowing down. The radio receiver then just interprets those changes in speed as the original sound. Pretty clever, right?
And here's the massive advantage of FM. Noise immunity. Since most natural static and noise affects amplitude, FM signals just ignore it. That's why FM radio sounds so much clearer and has that high-fidelity sound. The trade-off, it takes up more room on the radio spectrum, what we call higher bandwidth, and the technology is a bit more complex than good old AM. All right, our third and final technique is phase modulation, or PM, and this one's a little more subtle. Just like FM, the amplitude of the wave stays constant. But with PM, we alter the phase of the carrier wave. The easiest way to think of phase is as the rhythm or the timing of the wave cycle. We encode our message by making these tiny, instant shifts in that timing. So for our speedboat, its size and its average speed are constant. But to encode the information, it's making these tiny split-second adjustments to its rhythm, almost like a drummer who's subtly shifting the beat. It's a really sophisticated way to cram information into a wave. Now, PM has a lot of the same benefits as FM, especially that great immunity to noise.
And while you don't see it much in analog broadcasting, PM is incredibly important because it forms a foundation for so much of our modern digital communication. Why? Well, because those sharp, instantaneous shifts in timing are perfect for representing the ones and zeros of digital data. In fact, you're probably using a form of it for your Wi-Fi right now. Okay, so now that we've met each one individually, let's put them all side by side. It really helps to see the differences and understand the trade-offs that engineers have to think about. So here it is, a direct comparison. You can see AM, varying the amplitude, is the simplest but also the most vulnerable to noise. Then you have FM and PM, which vary frequency and phase. They give you that high noise immunity but are more complex and, in FM's case, need more bandwidth. This really shows that there's no single best way. It's all about picking the right tool for the job. So, why do all these technical details actually matter to you? Because this isn't just something in a textbook. This is the hidden technology that makes so much of our modern world possible. You really do run into these every single day. AM radio is still the king for talk radio and long-distance broadcasts where you just need to get the signal out there. When you tune into a station for music and want that crystal clear sound, you're using FM. And like we said, phase modulation is a critical building block for the digital signals that carry our internet data right through the air. So let's just quickly recap the big ideas here. First, modulation is absolutely essential for sending information over long distances. Second, it all works by having a message hitch a ride on a powerful carrier wave. The three main ways we do this in the analog world are AM, FM, and PM, which change the carrier's strength, speed, or timing. And finally, each one of these has its own unique pros and cons. Getting a handle on these analog ideas is a huge first step. But it also brings up a really fascinating question. If these techniques are all about smooth, continuous waves, how on earth do we use them to send the choppy, black and white ones and zeros of our digital world? Well, that's a story for another time. Thanks for joining us.